So a less commonly used technique in electronics, but still important nonetheless, is current division. Now, in the case of voltage division, we've seen that voltage division applies when resistors are in series. Therefore, we expect that when resistors are in parallel, we will have a similar sort of simplification that we can make. Before getting into the actual concept of current division, we should take into account we should consider first the conductance. So we define the conductance, let's call it G, as 1 over resistance. So any resistor with a resistance of R will have a conductance of G, and the units of this we call, well, for our case will be millisiemens, as we're defining resistance in kiloohms. So now that we have this thing conductance, we can take a look at Ohm's law, and Ohm's law tells us that V equals I times R. Therefore, if I were to plug in my equation for G, G is actually equal to 1 over R. So let's divide out on the left side. Well, let's get R to the left side. So I will have here now I equals V over R. Now if I flip the equation and I substitute for G, I will get that I is actually going to be equal to G times V. And so this is a sort of alternative form of Ohm's law in terms of the conductance. Now this is going to be important for the current division rule, since current division will happen when resistors are in parallel, and we know that we can add resistors in parallel using this sort of 1 over dependence of every resistance, where you have 1 over R1, 1 over R2, all the way to an n number of resistors where each resistor is connected in a sort of parallel connection. And so here you would have R1, R2, and Rn. And so now, if we examine this a little bit further, so I will need to redraw this a little bit bigger because we will actually have to do some analysis on this. I will consider a number of resistors in parallel. And again, as in the case of the voltage division, we're considering the general case where we will have n number of resistors in parallel. So I will call this R1, I will call this R2, and I will call this Rn. And now, in each branch, I will have, well, let's call this I1, let's call this I2, and let's call this In. And I will call this current flowing here I. So we have a total current flowing in, and we have a number of branch currents. Now the question is, how can we define each branch current in terms of some parameters that we know? So current division tells us that, let's say I1 is going to equal the total current I times G1 divided by G1 plus G2 plus Gn. And so now the thing to note here is that this is not the resistance, but this is the inverse of the resistance, which we call conductance. So I take the total current, multiply it by whatever conductance is in the first of the first branch, I should say, divided by the total conductance of the entire circuit. Similarly, I can define I2, or I can solve for I2 in terms of the conductance of the second branch. And the thing to note here again is that this is the conductance of the branch. Therefore, if I have multiple elements and I can lump them into a single element, then I can still use this rule. Which means in general, if I have an nth current In, this will depend entirely on the nth conductance, and this will be expressed as follows. So now let's take a look at an example, a very simple example again. So we will see here, let's say I have a simple parallel circuit with, let's say, 3 elements in parallel. And I'm going to define these conductances, or these resistors in terms of their conductances. let's say I have 1 millisiemens here, I'll have 2 millisiemens here, and 3 millisiemens here. And let's say I have a total current of 2 milliamps flowing in, and I want to know I1, I want to know I2, and I want to know I3. So by using current division, we can simply find these currents, saying that I1 is going to equal 2 milliamps. So I'm going to say, I can leave it as 2 because I assume all currents are in terms of milliamps anyways. And this will be G1 is going to be 1 millisiemens divided by 1 plus 2 plus 3. This is going to equal 2 over 6, which is going to equal 1 over 3 milliamps. You can write this as 0.333 or however you'd like. I'll leave it as an exact number there. Now let's take a look at I2. I2 is going to equal 2 times G2. So now the conductance G2 is 2. So I can write this as 2 over 1 plus 2 plus 3. Now in this case, I'll have 4 in the top and I will have 6 at the bottom, and this will become 2/3 milliamps. And now if I take a look at I3, well, I could solve this using a simple Kirchoff's current law at whichever node, and I will know that whatever current goes in must go out. However, let's use our current division, and then we can verify that after. So my total current is 2, my branch conductance is going to be 3, and this is over 1 plus 2 plus 3. And so this will give me 6 over 6, which is 1 milliamp, which is exactly what I expect since I have 2 milliamps going in. This 2/3 and this 1/3 will give me 1. This will give me another 1, and therefore I have 2 milliamps divided between these 3 branches. So you see, current division is useful whenever we have circuit elements in parallel, well, resistors in parallel, I should say, not any circuit element. But in electronics, this sort of approach, or these kind of elements, or this kind of setup, I should say, doesn't really show up that commonly. So it is useful, but it isn't the go-to method of solution. Most commonly, there will be using voltage division. But still, it's important that we understand this concept and we are able to apply it if need be. So I hope you found this video helpful. If you haven't already, hit that subscribe button, and we will have notifications for you as soon as the new videos are posted. And otherwise, we'll see you in the next one.